Good afternoon. Can you hear me? Can you see me? Because I was going in the wrong direction. I think I go a little bit besides the port so you can see me. My field of research is actually exomoons. And so let me first define what a moon is. The moon is actually the satellite which orbits Earth. It's the name we given to him. Another name for it is Luna. And it has its barycenter within the Earth. The system between Luna and Earth is the barycenter in the Earth. While Pluto and Charon is a system where the barycenter is outside the bigger body. So we are talking here about, what is it? A dwarf binary system, or dwarf planet binary system after Pluto is not a planet anymore. The other definition is a satellite has to be a body which is orbiting another body in the system which is not the central star. So now that we have that out of the way, let's talk a little bit about exomoons. There was a big announcement about half a year ago from TG et al. That they found an exoplanetary system in Kepler 1625, which was a Jupiter-sized planet with 10 mass of Jupiter and that had a Neptune-sized moon. The moon was orbiting about 20 planetary radii away from the planet. It was a very exciting announcement. There were follow-up observations in October, and we haven't heard anything since then. So it's most likely it was a fluke in the dark. If you look for exomoons, the problem is they are very, very, very hard to find. If you look at transit data, for example, you have an exoplanet, you can fold it, you can bin it, you can run your Fourier transformation and your long Lagrange of it, and you find your exoplanet. In the moon, you have to look at each transit itself because you don't know where in the orbit around its planet the moon will end up. So far, we are not very lucky. Which is good for me because I can tell you everything, you can't prove me wrong. However, think about it. If we have the same amount of moons which we find in our own solar system, the amount of habitable moons would be much, much higher than the amount of habitable planets. And to be habitable, we need an energy source. We have talked a lot about the habitable zone. I talk about Europa here, and I look at the energy which is provided by tidal forces to Europa, which is about 1500 terawatts. So if you put it on the surface, which doesn't make sense, but it's just a number to compare, we would have about 250 kilowatt per square meter on energy. But this energy is within Europa and makes it possible that it has an ocean underneath, a very bright and big 10 to 30 kilometer thick ice crust. You see here the energy provided into Europa by tidal dissipation is about 1500 terawatts. Which brings me, as I don't have found any exomoons, to another thing I had to look at. So I followed up this guy here. I think they all know him. Galileo, we see him here, approaching for a research plan with the two children on tennis. Same situation, nothing has changed in the last 200 years. He did his research notes by hand, then he corresponded with some and cooperated and collaborated with some other scientists. And in the end, he satisfied the Deputy Vice Chancellor of Research and published his findings in a Q1. He called his moons, being known as Galilean moons, the Medicia Siderea, which means he pleased another one of his benefactors who gave him money for his research, the Medici family, who helped him do the research. However, when he pointed his telescope the first time to Jupiter on the 7th of January 1610, he found the Galilean moons. We know them today as Io, Europa, Ganymede, and Callisto. Jupiter Jupiter has a very extensive satellite system. In total, we know now about 69 satellites, where the inner satellites are in in prograde orbits around Jupiter, very close to it, and then we have the irregular satellites. We are very, very out in retrograde orbits and not really close to Jupiter. So I looked at the orbits of the Galileans because I wanted to know if they are stable. We see here 100 years eccentricity plots. This one is now, this one is in 50 million years, this one is in 100 million years, 150 million years, and 200 million years. And as everyone expected, nothing really changes with the Galileans. They're quite stable. They are in resonance. We heard that before, and I will not go, because I'm running a little bit out of time, I will not go in detail in that, but they are in a 1 to 2 to 4 resonance. Even if we look at 10 million years, at 10,000 years, now and in 50 million years, in 100, 150, and 200 million years, we see that the eccentricity is oscillating a lot, but it's relatively stable, and with the Galilean moons itself, it doesn't change anything. However, there's a different story if you look at the inner four moons. Here again, we see the Galileans, we see the orbital period, and yeah, nothing really happens. But if you look at the inner moons, especially at Agastea and Metis, we see that in about 18 to 20 million years, something dramatically is happening with the eccentricity of Agastea, which goes completely out of whack. And if you look at the orbital period, we see that Agastea and Metis have changed places. All of a sudden, Agastea is the inner moon, and Metis is the outer moon. I looked a little bit closer at the orbits, and if you look here, you will see again now, and then the 200 million year mark is here. Right now, the axis will go a little up to make it a little more visible. You see, Agastea has completely changed its inclination, its eccentricity, and its orbit. However, I think this data after 20 million years is meaningless because I think my data shows that they will have a collision by then. So again here, you see this collision point, and the data afterwards is, I think, not really relevant anymore. So if you look a little bit closer at the moons now in 18 million years and in 50 million years, you see that the orbit of Agastea and Metis are overlapping. And this overlapping causes most likely sooner or later a collision between the two. And yeah, well, then we have just 3 inner moons of Jupiter. I was also looking into a little bit earlier, that's about 250,000 years. You see that both have a close encounter and change orbit about 200,000 years ago, recover, and in 20 million years ago, 20 million years in the future, not ago, they will collide. It's a very interesting finding because if you think about it, the ring of Jupiter is made of the same material than Agastea and Metis. You see the albedo, we think it needs to be replenished all the time, and that mechanism is thought of happening with impacts of meteorites at the moons. However, my orbital dynamic simulations, I started them when our HPC was idle for a month ago, and I did about 200 billion orbits of Metis. Shows that there might be another mechanism responsible for replenishing the rings, which is close encounters between the 2 moons. That's it.